Hi, welcome back to Sound School. This is part 3, the Intro to Signal Processing. So now that we've learned what a sound is and how it becomes a signal that gets into our equipment, it's time to start manipulating it. And this phase of our work is called signal processing. As we already know, signal is the electronic version of acoustic sound pressure that has been converted to electrical energy and is now traveling as electron flow through our audio equipment. Now it's ready for us to adjust as needed to make our mix exactly the way we want. Before we go too far into this, I want to be clear that there are no rules for how we use signal processing. You can and should use this stuff however you like, either in creative and adventurous ways, or subtly and carefully to preserve the original sounds. Whatever you see fit that will get your desired outcome. Try things and see what happens. Don't assume something will sound a certain way on your project just because it worked like that on someone else's. Try it, listen, and then decide for yourself if the result is what you want. Sometimes using something in an unusual way can have great results, so feel free to do things that might not make sense. There are no rules, only laws of physics. And those laws will dictate how the equipment functions on the signal, but there's no telling what the result will be on your specific sound until you give it a try. So the very best thing you can do is know and understand the laws of physics and the functions of your equipment, and then go ahead and make your own rules for how you use them. In your work, you'll encounter signal processing in 2 different forms: analog and digital. Analog processors are the real-life equipment units, also called hardware, made up of electronic components like resistors, capacitors, diodes, transistors, among other things. And these components manipulate the electronic current. They use various methods of restricting, redirecting, or amplifying that current in order to change the sound. When you grab a knob on the mixer and turn it, you're affecting the flow of electrons inside. Now, digital processing manipulates the sound signal once it gets inside a computer as digital information. To use this kind of processing, the electronic version of the signal is passed through a converter and translated into digital information, ones and zeros, or digital code. And then the computer manipulates that digital code to alter the signal. This is what's happening with your audio software inside of your plugins. When you click your mouse to turn a knob on the screen, it's adjusting the digital code. The best kind of signal processor to talk about first is equalizers, or EQ for short. We encounter EQ all over the place in our day-to-day lives, probably without even thinking about it. Every time you get in a car, you probably turn on the stereo. And you might immediately look for the tone control, probably to turn the bass up. That's EQ. On your stereo at home, there's probably a place to turn up the highs and the lows. That's EQ. With your earbuds or your headphones, you probably have an app in your phone with an equalizer on it that's processing the audio to get it the way you want it to sound. There are lots of different reasons to use EQ. We use it to improve the overall sound quality of something, or to remove unwanted noises or tones, or to enhance desired noises or tones, and finally to help blend multiple sounds together. So let's get into what's going on when you adjust these controls. Now, as we already know from previous lessons, amplitude is the height of the waveform, which determines the perceived loudness of the sound and is measured in decibels. And then frequency is the rate at which a sound wave repeats, which determines the pitch and is measured in cycles per second, called hertz. So to really understand this, we're going to use a graph that shows both of these units at the same time. This is called a frequency response graph. Up until now, we've looked at waveforms on a graph that shows them flowing over time. But now we're going to look at a capture of sound waves at a moment in time. On the vertical axis, we still have amplitude in decibels, but this time the horizontal axis shows frequency in hertz. To the left is the lower frequencies, moving to higher frequencies as we look to the right. Frequency response charts show the spectrum of human hearing. Human hearing runs from 20 hertz at the lowest, 20 cycles per second, up to 20 kilohertz at the highest, 20,000 cycles per second. Most humans can't really hear all the way up to 20 kilohertz. Maybe a baby can when it's first born, but by the time you're an adult, it's highly unlikely that you're hearing anything beyond 15 or 16K at the most. Now, 20K is still valuable because even if we can't fully hear it, it can add clarity to the rest of the signal. This is a concept that we'll dig into in future lessons. For now, you just have to understand that the frequency response chart shows 20 Hz to 20 kilohertz because it makes a nice even graph with 1K right in the center. This makes it easy to read in order to understand what the sound we're looking at on the graph might sound like in real life. For example, if we look at this, we can guess that it's boomy, humming, or thumping. And if we look at this, it's probably shrill or piercing. We can look at the frequencies on the x-axis and think to ourselves what the ranges that are represented must sound like when heard. Here's a special tidbit about the laws of physics related to sound. It's called the Fletcher-Munson curve, or equal loudness contours. Fletcher and Munson were a couple of scientists in the 1930s who were studying human hearing and the fact that humans don't hear frequencies the same way at different volumes. When something is louder, we hear the frequencies differently than when it's played back more quietly. This means that human hearing is non-linear. When we listen to the same sound but louder, our ears actually hold down the mid-ranges and turn up the highest and lowest frequencies. This is an evolutionary tactic designed to protect our eardrums. Our ears are the most sensitive to mid-range frequencies, something we developed to be able to distinguish voices and speech. And so when we hear higher sound pressure levels or louder volume, our ears protect themselves in that most sensitive range. And then when we hear the same sound but quieter, our brain turns up the mid-range and turns down the lows and the highs. It's the same evolutionary tactic at work to help us distinguish speech and voices over other quiet sounds. So here's our frequency response graph showing a sound that's pretty flat across the spectrum from 20 to 20, showing it at 80 dB SPL, a nice average listening level, which also happens to be the SPL level at which our hearing is flat, or linear. Now, if we make that sound louder above 80 dB, let's say 100 dB, our brains will perceive the higher and lower frequencies as louder than the mid-range. And then if we make that sound quieter, let's say 50 dB, our brains will hear less of the highs and lows and more of the mid. So you can see how this would be valuable to keep in mind when you're processing audio and making decisions on how it sounds. Always be thinking about how loud the sound is that you're working on and how loud it will be in the finished product. And remember that the way that you perceive it while you're working on it could affect the way that it's perceived by the listener when you're done. This concept of Fletcher-Munson and equal loudness contours was so important to me that I even named my cat after it. We're going to start with the type of equalizer called a graphic EQ first, because it's the most commonly encountered equalizer type in consumer audio equipment. There's basically no way that anyone has made it past the age of 10 without encountering a graphic equalizer, be it in the car, on the stereo, or in your television or computer. You'll recognize a graphic EQ because it will have some small faders. Here's an example of what you'll see either on a piece of hardware gear or on a screen in an app or car stereo. You'll have some number of faders, usually 3 for a really basic system, that sit at a middle point and give you the option of turning them up or down. So if we look at this unit on the frequency spectrum, we can think about what's happening to the sound. Here's our spectrum, 20 Hz to 20 kilohertz with 1K in the middle. And if we push our mid fader up, it will make a boost in the frequencies in the middle. We can push the low fader up and boost the bottom frequencies too. And in turn, if we pull the high fader down, it will pull the high frequencies down or cut them. And our end result is a changed frequency response for our sound. When we start to get into more professional audio equipment, we start to see units that divide the spectrum into even more frequency bands. Here's one that shows faders at every 1/3 octave. This allows us to get a lot more specific with ranges of frequencies we can turn up and down across the spectrum. As you might recall from our earlier lesson on frequency, 1 octave up is double the frequency, and 1 octave down is half the frequency. Octaves act as harmonics to fundamental frequencies, providing overtones and undertones in our sounds. As well, when sound is bouncing around in a space, rooms will often resonate at points an octave above or below the primary sound. This is due to the fact that for a frequency that resonates in a space, one that occurs at exactly half or double the length will also resonate in that same space because of the size. Therefore, having the bandwidths broken into thirds allows us to quickly identify the next octave point above or below the frequency that we're working with. As well, if we're not exactly sure which frequency we need to adjust, we can reach for a fader at the approximate area of the spectrum and test out faders in that area until we're sure we have the right one. One specific application of this style of graphic EQ is in live sound. In live sound, graphic equalizers are typically placed between the console's final mix output and the overall sound coming out of the speakers to allow you to be able to quickly and easily adjust the mix with the specific resonances of the room. Specifically, in the case of the monitor engineer, who is mixing the sound coming out of the speakers on stage that the performers are listening to, each monitor speaker will have its own dedicated graphic EQ, so that the engineer can use it to quickly and easily eliminate frequencies that are most likely to cause feedback. Feedback, of course, is that squealing, screeching sound that happens when we put the sound from a microphone through a speaker, and then the mic picks up that sound as it comes out of the speaker. The sound system keeps playing the sound through the speaker, and the mic keeps picking it up over and over until it becomes a loop and it starts to scream. The frequencies that end up feeding back will be those that arrive in phase from the speaker into the mic, or out of the speaker off a wall into the mic, or out of the speaker off the brim of the singer's hat and into the mic. As we know, when a frequency is in phase, it doubles the amplitude. So frequencies that are the right length to be in phase in this situation will just keep doubling over and over and will become louder and louder than everything else. But if we can identify those frequencies and turn them down with our graphic EQ, we will stop the feedback loop. Up next, we're going to look at parametric equalizers. The term parametric refers to the fact that this type of EQ has additional parameters that can be manipulated. On our graphic EQ, each fader is set to a specific frequency, and all you can adjust is the amplitude, up or down. On a parametric EQ, there are more options. In addition to being able to adjust the amplitude of our frequencies, parametric EQs also allow us to move the frequency point that we're adjusting. So let's look at an example. So here's a knob for adjusting our amplitude. It's doing the same thing as the faders on the graphic EQ, just shaped differently as a rotary knob control instead of a slider. You can see that if we turned it to the right, we would turn up the amplitude or the loudness. And if we turn it to the left, we will turn down the amplitude or loudness. And then on our parametric EQ, we have another knob for the frequency. This one is going to let us adjust the frequency of the mid-range. We can choose a position anywhere between 250 Hz and 6.3 kHz. Wherever we point the knob will determine the frequency that the amplitude knob boosts or cuts. My console here has parametric EQs. The real advantage of a parametric equalizer is that it allows you to scroll through the frequencies or sweep through them one after the other to find exactly the range you're looking for. So let's give this a try. I've actually got some music queued up, ready to go. So I'll just start it playing and then I can fade it up into our mix. Now we can turn the amplitude of the mid-range up all the way and then sweep through the frequencies from one side to the other. And if we put that back, we can move down to the low band, turn that all the way up, and sweep through from the bottom and up. And now we can do the same with the high frequency. And this way we can listen to all of the frequencies one at a time as we sweep through them. And that's how you sweep for a frequency with a parametric EQ. So this EQ on my console is only called a semi-parametric equalizer because it only has 2 parameters in 3 bandwidths that you can sweep. A fully parametric equalizer will have the frequency control that lets you sweep on the high, high-mid, low-mid, and low bands. This way you can sweep all the way across the entire spectrum. And this will let you find the exact frequencies that you need to adjust. Now, a fully parametric equalizer will also let you adjust the bandwidth, which means the width of the range of frequencies that you're adjusting with the amplitude control. This is called the Q width. You can use your Q control to make the width of a band wider or tighter. If we look at this on our spectrum graph from 20 Hz to 20 kHz with 1K in the middle, and we boost at 1K, this control will let us choose how many frequencies on either side we are manipulating along with our center frequency of 1K. More frequencies or less, wider or tighter on the spectrum. Now you have to watch out because this control is based on physics and electronics and ultimately math. The control itself is specific to the math involved, and so some kinds of equipment will label them differently. You might look at a knob on your console and notice that there's a higher number to the left and a lower number to the right on your Q control. In this case, the higher number actually means a tighter Q, and the lower number means a wider Q. Sometimes manufacturers and designers are kind enough to include a little drawing of a tight peak or a wide curve to remind us, but sometimes you just have to know a higher number Q width is a tighter bandwidth. And now you know. A filter is a type of EQ that restricts the frequencies above or below a specified point. So on our spectrum, we could have a filter restricting the low end or the top end of our signal. When we filter out the low end, we are allowing the high frequencies to pass. And we call this a high pass filter or a low frequency roll off. We are rolling the lows off or letting the highs pass, but both result in the same effect of reducing the low frequencies. This is great for quickly removing unwanted sounds, like wind noise or air conditioner hum, or even ground hum in your system. It's also great when someone talking directly into a mic says words with P's or B's, and you get that rush of air over the mic that makes a rumbling sound. You can quickly filter out those low rumbling frequencies with a high-pass filter. You'll often see it drawn on your switches and buttons on your console as just a little line that looks the same as your frequency spectrum chart. Now, at the other end of the spectrum, you have the high frequency roll-off, or the low-pass filter, which restricts the high frequencies and allows the lows to pass. This is a quick way to eliminate high frequency feedback, or take out that high hiss that's sometimes caused by the noise floor, or even the sounds made by fluorescent lighting or electrical power supplies that sometimes get picked up by microphones. A switch for a high frequency roll-off or low pass filter will have a little diagram that looks like this. Again, looks just like our spectrum chart when we're using this switch. And then you'll also encounter a type of EQ called a shelf. And this is just the boosting version of a filter, where you can shelf up the low and high bands above or below a specific frequency point. This can be helpful to create deep sub-resonances, or to add air and clarity to high-fidelity content. It's also worth noting that these filters are sort of on the road to becoming kind of obsolete. There are a lot of plugins and types of equipment being made using AI, and other high-tech algorithms, which can identify these unwanted sounds and remove them automatically, or identify desirable bandwidths and boost them automatically, without us necessarily having to understand the process. However, you'll be at a huge advantage when using these devices if you actually know what they're doing and why. There will always be value in knowing the physics and technology behind the convenient modern tools. This will allow us to make the best and fastest decisions on how and where to use them.